Hello, everyone. I think we can start now. I think most of the people that want to come live are here and in the Zoom meeting. So first of all, welcome. Thank you for attending. And my name is Fisnik Zenulahu. I'm the system engineer, one of the 3 system engineers of the project Aquila. Today we are going to show you our preliminary design, and the goal of this design review is for us to get some feedback on our rocket and ultimately to know our design a little bit better. First of all, because there are some people that are here that probably are not very much in touch with our project at all, I'll give you a brief overview. What is Aquila? Our rocket Aquila, you can see it on the right side here. It's a rocket that will be attending at the SAC, which is the world's biggest rocketry competition. And the goal of these competitions is to reach a certain height as perfect as possible. So we are building this rocket, and we're going to start it next year in June. And yeah, so that's the general overview over the project. First of all, a brief agenda for today, a quick introduction about some general topics, and then we're going into the system data, and afterwards we're going to go more in detail into the system architecture of the different subcomponents. So let's start with the introduction. First of all, this is the team. We're consisting of 22 members, of which 3 are mentors, 3 are system engineers, 3 simulations, and so on. You can see that. And we have split our project in different subsystems. So we have simulations, structures, recovery, and avionics. This is the timeline. First of all, we started with an internal PDR, preliminary design review, in July. And now we're at the external PDR, so we are presenting our project to external members that are not in the space team, and furthermore, now we are in the SAC application phase. So till the 15th we can apply for the SAC, and then we can start next year. In January, we will have our critical design review, so that's something like this, just that after the critical design review, our design will be frozen. So afterwards, only the production and the assembly will take place, and when the rocket is produced and assembled, we will then have a rollout event where we will present our rocket to the sponsors, to the space team, and also to certain other people. Yeah, and then on the 19th of June, we are going to be in New Mexico to start our rocket at the Spaceport America Cup. Hopefully, if all goes as planned, our rocket will land again, and then we can participate at the European Rocketry Challenge, which is the European equivalent to the SAC. Some words on financing and sponsoring. This project especially needs big funds because, of course, we're going to have to go to America, so that's not cheap. But we already got some funds. We're still missing 11,000 euros, so that's the challenge for the next few months. These are some of our sponsors and supporters. Yeah. And with that, I'm going to give to Tobias.
Thank you. So first off, I want to thank you for attending the presentation, whether it's in person or by joining the Zoom session online. My name is Tobias, or Tobias, better, one of the system engineers, and I want to talk with you about the key requirements that need to be fulfilled in order to participate at the Spaceport America Cup. Also, I want to talk about the rocket design in general and our flight profile. So we divided the requirements in general requirements and in specific flight requirements. So usually these kind of rocket competitions are divided in 2 categories. you have a 3 and a 9 kilometer apogee categories, so you try to reach the targets as precise as possible. So since the space team Aachen already flew 2 times in the 3 kilometer category with Carl 1 and Carl 2 at the European Rocketry Challenge 2020 and 2021, we set a new goal to fly in the highest possible category. So therefore, we will apply for the 9 kilometer range with a commercial off-the-shelf engine, so basically a bought engine. Also, additionally, we need a functional payload with at least 4 kilograms, where 3 kilograms need to be the actual payload, and 1 kilogram could be a dummy mass, for example. Furthermore, we need to have the recovery system successfully tested until the 1st of April. Let's go to the flight requirements. So we need to have a stability in between 1.5 and 6.0 calibers. So the unit calibers here refers to the diameter of the rocket. So for everybody who doesn't know exactly what stability means, we have a little picture here, and I can show you. So we have the center of gravity, here marked in blue, which is basically the average location of the weight. And we have the center of pressure marked in yellow, CP, which is the average location of the pressure which is applied. So when basically why do we have to go into this range of 1.5 and 6.0 calibers, one could ask. So when you're over 6 calibers, the rocket is referred to being overstable. So then the rocket is more likely to move into the wind. So that's something you don't really want. And when your stability is under or below 1.5 calibers, the rocket tends to turn, or even could turn towards you. So that's something normally you don't want or you want to prevent. So let's see, we have now here measured the stability. That's 1.5 calibers, so that's basically 1.5 times the diameter of the rocket, and that's the distance between these both points. So when, for example, the motor starts to burn, you have a movement of the center of gravity upwards, and therefore the stability also increases. So it's not a fixed value. When the velocity increases of the rocket, you have a movement of the center of pressure downwards, and therefore the stability increases. So you can see even when the velocity increases further, the center of pressure moves up again. So you can see the stability is not a fixed value. So it's you have to keep that in mind when calculating it. Yes, that's it for the stability. We also need to have a dual event recovery system since we are above a certain threshold of height. So we need to have our drogue parachute deployed near the apogee. And when the drogue is deployed, we need to have a descent speed of in between 23 and 46 meters per second. We also need a main parachute ejection, which needs to happen below 457 meters. And the speed should be below 9 meters per second with the main deployed. So let's go to the design in general. That's the rocket. The rocket will be 3 meters in length, and we will have a diameter of 11.4 centimeters. Our wet mass will be, so that's basically the mass with the propellant, will be around 31 kilograms, and the dry mass without the propellant will be around 20 kilograms. So next up, I want to talk about the different sections of the rocket. Let's start with the nose cone of the rocket. So that's the nose cone part. and the nose cone consists of the nose cone body itself and the tip. So the nose cone tip is made of aluminum and functions basically as a heat absorber. Also, we have a thermal and a pressure sensor located there. And we have the tower, the Avionics tower, so that's where the Avionics is located, inside the nose cone. We also have 3 cameras that provide 360-degree recordings of the flight. And also, of course, we have camera hatches, so the cameras can record properly. So, yes. Next up, we have the recovery bay. So you can see we have here something called the nose cone bulkhead. So every time, so bulkheads basically connect and separate different sections of the rocket. So therefore, they allow an easy access of each section. And we have the convention that when we call the bulkhead the nose cone bulkhead, that's basically the bulkhead below the nose cone. So when we talk about the recovery bulkhead, that's the bulkhead below the recovery bay. So every time we talk about the bulkheads, you hopefully now know which one we are referring to. Inside the ejection, or inside the nose cone bulkhead, we have the ejection system located. And we have the parachutes also located inside the recovery bay. Okay, let's go on. We have there the recovery bulkhead and one of the launch lugs. I will elaborate on that later. So afterwards, we have the payload section. For the payload, we have different options currently. One would be a sloshing experiment, one would be a cooling experiment. That part still needs to be fully developed, so we won't elaborate on that for now. We have the payload bulkhead below the payload section, which again connects the payload section with the engine section. So obviously in the engine section we have our solid engine, and we have the fins, which basically stabilize the rocket. They are attached to the engine tube. And we have our engine bulkhead, where the second launch lug is located, is attached to. And yeah, we have, so these are the both launch lugs. I can show you here. So one is here, and the second one was there. So yeah, they're basically there to guide the rocket on the launch rail. The engine bulkhead connects the boat tail to the engine section, and the boat tail serves to reduce the drag during the flight and to hold the weight of the rocket when it stands. So next up, some details on the motor. We have a Cesaroni N-class motor with approximately 19 kilonewton seconds total impulse, 5.8 seconds burn time, and 5 kilonewton peak thrust. That will lead to a velocity of approximately Mach 1.8. We will reach an apogee of 9.3 kilometers and a maximum acceleration of 15 g. We will also have a stability of between 1.5 and 4.9 calibers, so therefore we meet the requirements I mentioned. Okay, that's it for the design part. Now, next up for the flight profile, we have a nice little animation prepared. You can see the time here, the event, the velocity, altitude, and stability of the rocket. So we will go through each event during the flight and mention some numbers. So that's the rocket on the launch rail. Yeah, first off, we have, of course, the liftoff, where we will have a stability of 1.5 calibers. After liftoff, we will reach maximum velocity after 5.3 seconds. There we will reach the mentioned velocity of 1.8 Mach. We will have a stability of 2.9 calibers at that point. After 5.8 seconds, we will have the motor burnout at an altitude of 2,000 meters. After that, we reach the maximum stability after 9.7 seconds. We will have the stability of the mentioned 4.9 calibers. After 40 seconds, we reach the apogee. That will be about 9,300 meters. The drogue parachute will be deployed after 41 seconds after liftoff. And afterwards, we will have a velocity of minus 24 meters per second. So that's the velocity we will have with the drogue parachute ejected. So after 308 seconds after liftoff, the main parachute, as maybe I can repeat that, the main parachute will be ejected and inflated, and we will reach the velocity of minus 7 meters per second and hopefully land in one piece this time. Yeah, and that's it for the flight profile, and that's it for my part. So next up, Johan will present the system data. Unfortunately, Johan cannot be here today in person, so he will present online. So wait a second, Johan. I will tell you when you, okay. Wait. War eben oben immer, oder wo war das?
Okay, is it ready?
Yes, we're ready.
Okay, perfect. Hello everyone, my name is Yuan, and I am the lead of the simulations sub-team of the Aquila project. And today I'm going to be going over the system data with you. First of all, before we begin, I suggest all attendants on Zoom to pin the Aquila stream on their screens so that you can see the presentation and everything. And you'll be able to see me on that screen as well. So with this, we begin with the system data. My part of the presentation will consist of presenting you the simulation models we used. We'll go through the flight profile, the force profile. We'll take a look at how the wind influences the rocket. We'll do a short software comparison, and we'll check with the next steps of the simulation sub-team. With this, we go to the next slide, please. First of all, we will take a look at the simulations models we used. Up until this point, two main software were used to analyze the trajectory of Aquila. One of them is OpenRocket, the other one is RockSim, and we want to compare those softwares as part of our research. So the main challenge of Aquila is that it's going to fly supersonic, and OpenRocket and RockSim are not that precise at supersonic velocities. So that's why we want to develop a method for the space team Aachen to tackle that problem and to be able to adequately estimate the flight profile of any of its future supersonic rockets. So for those models, we used CAT data, and we tried to estimate the weight and the center of gravity as precisely as possible. Our target is with these analysis tools to reach predictions within 5% of the real data, and then upgrade them to hopefully become as precise as possible. We go on to the next slide. And the first topic is the total motion. So the total motion profile is just as expected, as you can see on the graphic. In the light blue curve is the acceleration of the rocket. So that's the acceleration magnitude. And you can see the maximum acceleration is achieved very shortly after the motor starts. That's classic for every solid motor. The peak thrust there is 5.3 Gs. With that, we start to accelerate the rocket and up until it reaches its maximum velocity shortly before motor burnout. Um, After that, we reach yes, the red curve is the total velocity. After that, we reach the motor burnout, and then we start to decelerate because of the drag we experience on the rocket. Nevertheless, we still fly higher, and we reach our apogee at 9,356 meters above ground level. After that, we start our descent, which is a bit stretched in so that we have a place for the more important, for the more detailed parts of the graphic. And after that, we have our other large acceleration point, which is the main parachute deployment event. Uh, this doesn't occur at 2.5 speeds, but the drag increase is really significant, leading, according to the simulation software, to 11.9 Gs of deceleration loads on the rocket. Next slide, please. Another very, very important task of the simulations team was to determine the stability and make sure it complies with the requirements given by the organizer and by the team itself. So the red curve here you see is the stability of the rocket. What is important to note, it depends on the center of pressure and on the center of gravity, as Toby explained, and the center of pressure itself depends also on the Mach number, on the velocity of the rocket. Our lowest stability is achieved right after we leave the launch rod, where the rocket for the first time is on its own. So we're starting to calculate the stability right after that, and at this point it's a bit above 1.5 calibers. Then it increases after we surpass about Mach 1. I believe Mach 1.4. The center of pressure drops back forward, which brings the stability to lower levels, but it's still nothing too significant. It only dropped to 3 body calibers. After that, we start to slow down. With this, the stability increases again. And then with further slowdown in the subsonic region, it decreases further until it reaches its final values. Next slide, please. Another important thing is, of course, to determine the drag coefficients. This will be properly done with CFD analysis, but we still wanted to show the analysis from OpenRocket. As you can see, we have a base drag coefficient, which is marked in dark blue. We have a friction drag coefficient, which is the light blue line. This is more at subsonic speeds and less at supersonic speeds, which is to be expected. That's what theory says as well. And we have in yellow, the yellow line is the pressure drag coefficient. The pressure drag, also known as wave drag, increases after we get to subsonic speeds. This is also quite logical. This brings us to the red line, which is the total drag coefficient. This varies between 0.51 and 0.66, which could be plausible, but still we want to make sure that the drag coefficient calculation is as precise as possible. And for that purpose, we're going to use CFD. Next slide, please. Yes, the force profile. We analyzed the force profile up until, well, actually we analyzed the whole force profile, but recovery has better calculations on the force profile with the chute deployment, so we're not showing that here. We want to show the thrust force, which is marked in blue. This is as given by the manufacturer and is absolutely one-to-one correct. So the maximum net force is achieved at the very beginning. Yes, at the very beginning, with the blue line achieving almost 5,000 newtons, to be precise, 4,949 newtons at the very start of the burning time of the rocket. do not get confused. The drag force is plotted on the right axis here, so it's not actually higher than the thrust. Then we accelerate and we reach our maximum velocity shortly before motor burnout. And shortly before we reach our maximum velocity, we reach the point of max Q, which is the point of maximum aerodynamic load the rocket experiences. This is almost 900 newtons according to Open Rocket. Then the other large force acting on the rocket is at the main parachute deployment event, where also the large deceleration is. This is calculated by the recovery team to be 1,771 newtons of force, like the peak force of that event. And then we land the rocket at about 7.05 meters per second, with about 20 kilograms of mass, which leads us to having almost 500 joules of kinetic energy at the landing. Next slide, please. Last but not least, we are expecting winds at the launching pad, at the launching site. So we have to, of course, take into consideration the wind effects on the rocket. We tested different wind speeds and wind profiles based on more or less real world forecast data for the region we're starting in. So the wind velocities are increasing with the height, and here the plot shows the angle of attack and the orientation of the rocket versus the time at the maximum kind of extreme case we are expecting, which is 8 meters per second wind velocity at start, which is the maximum wind speed allowed by the organizer of the event, and then the wind profile gradually increasing according to the weather forecasts. So with this, you can see the dark blue line is the angle of attack of the rocket, which is the most significant, actually the only significant part for the forces we will experience. And this you can see first it's almost negligible. Afterwards it starts to grow, and then at lower velocities it reaches higher amplitudes, with the highest amplitude about almost at the end of the ascent part of the flight at 7.5 degrees, but the frequency there is a lot less than it is on the earlier stages of the flight, and this frequency is 0.3 hertz. 3 hertz. So for now, we don't think this is a concern, but we still have to consider this in our CFD analysis and calculate the forces and the bending moments acting on the rocket at these points. And another thing to see from this graphic is the red curve, which is the vertical orientation versus the time. And as we see, the vertical orientation changes gradually and kind of exponentially at the end towards horizontal position, which is as expected and proves that the rocket is never overstable. If the rocket were to be overstable, the horizontal orientation would occur kind of earlier before apogee and at higher total speeds, which is going to be very difficult to handle and pretty dangerous for the recovery system ejection. So there is no overstability, and this is verified through the wind analysis. With the next slide, we go to the comparison between those softwares. So now we concluded the analysis of the rocket trajectory and the flight characteristics. We're going to take a bit of a dive into the comparison between those software we used. First of all, it is noteworthy that there were almost no two significant differences. By that I mean all other differences than the two plotted here were in the 5% margin, and that includes the altitude, the total velocity, the total acceleration, the forces, and everything else. which is good. We put two identical rocket models, which we saw in the beginning, into both software and wanted to see the direct comparison between those software. And the biggest differences between them are at the drag coefficient calculation, which you can see at the upper graphic. This is quite different, and again confirms the need of of um, implementation of a CFD software to determine the drag coefficient as precise as possible. And then on the graphic at the down, the bottom graphic, you can see the center of pressure comparison. The center of pressure on the rocks in this is a bit weird in our opinion, because it doesn't vary as the speed of the rocket goes to the supersonic region, and and even before that, it almost doesn't vary. It just varies a bit at the end, which we believe is not intuitively correct. So we'll also take a deeper look at the center of pressure when we do the CFD analysis. With this, next slide, please. We'll go to the timeline for the simulations team from now on. Now we're at October 2022. By the end of 2023, we want to be ready with the most part of the analysis. So now our main focus will be to do the CFD and get those results well verified. This will open the door for us to use Astos, which is another trajectory calculation software. Its results will depend heavily on the CFD analysis. So we also want to compare that to the last two software. And parallel to that, we'll perform Monte Carlo simulations to determine where do we expect our rocket to land in which conditions. After that, at the beginning of December, we want to start doing wind or water tunnel testing to verify the CFD results we got and to verify that the solver is trustworthy that we're going to use. At January, we have our critical design review, and after the design is frozen and the other teams going to the manufacturing phase, we're going to try and gather as much as possible real-world data inputs, including from the tests from the other teams, so that we can try and go the most precise we can with our simulations. That is from my part, and now I'll hand over to Yanis from the structures team.
Thank you very much, Johan.
Hello. Hi guys, thanks for coming. My name is Yannis. I'm the lead structures engineer, so I'll be the one to guide you to the structure parts of today's presentation. Within structures, we have divided the rocket into different subsystems, which include the nose cone, body tubes, bulkheads, bow tail, fins, and launch lugs. And one of our goals was to basically design a highly modular rocket. And here you can see another overview, as Toby already went through the general overview. I'll not go into detail with this right now, but what I want to point out is that there's 4 different sections where we can easily disassemble the rockets to access the internal systems. Moving on. This is our nose cone design. It features a nose cone tip, a nose cone avionics tower, nose cone bulkhead, and it also features 3 camera hatches for the cameras that the avionics team is going to implement. The nose cone is von Karman shaped, which serves the purpose of minimizing the drag. It also mounts the avionics and the recovery system, so it's quite an integral part because it serves many purposes. As mentioned before, it has 3 camera hatches. It's a modular design, meaning we can easily take the nose cone off from the bulkhead by unscrewing basically only, I think, 8 screws. And also the bulkhead in itself is modular. The entire length of the nose cone will be 675 millimeters in length. It will be 3D printed using glass fiber reinforced polyamide. We did do a length simulation of the nose cone, and basically, as you can see, we are right at the sweet spot, which I think is quite optimal. So yeah, that's nice. The nose cone tip will be made of aluminum. I think that has been mentioned before. It will be turned, and yeah, as you can see, it's not a very complicated part. However, the avionics tower is quite a bit more complicated. It will mount the entire avionics system. It features space for 3 camera boards, the 3 cameras, the Telemega recovery board, the self-developed recovery board. It has battery boxes, and it features 2 arming switches. Moving on to the nose cone bulkhead. The nose cone bulkhead is basically where we mount the nose cone, the recovery system, and the avionics tower too. So it's it pulls, basically this is the part that pulls the different subsystems all together. This shoulder has a length of 120 millimeters. So that will basically be the length when the gas is expelled from the nose cone ejection. That's the length over which the gas can accelerate the nose cone. We already tested this, and it works out nicely, so we're confident in that dimension. This bucket design will contain the entire ejection system, and this is what that will look like. It's a little bit complicated, and as I'm just a dumb structures guy, I leave that to the recovery team to explain. Here are our body tubes. We have 3 different body tubes: recovery, payload, and engine tube. They will be manufactured using carbon fiber reinforced plastics with a length of roughly 1.6 millimeters. A thickness of 1.6 millimeters. The maximum length will be the engine body tube with a length of 1.2 meters. And we will be using use case specific manufacturing techniques. What do we mean by that? Basically, we wrote an entire project thesis about this topic where we compared 3 different manufacturing techniques for producing body tubes. One of those we disregarded, but we selected 2. The first one will be row wrapping, which basically looks like this. You take a mandrel and you use a pre-preg material around it. It's quite simple. And the advantage is that in that case, the inner diameter of your body tube will be defined, and you have very high inner surface quality compared to the outer surface quality, which is perfect for our recovery tube, as this needs to create a very tight, not a tight fit, a good fit with the nose cone bulkhead. On the other hand, for the other 2 tubes, we selected split molding. This is what that looks like. In that case, the outer diameter is defined, and you have very high outer surface quality, which I think Fisnik is passing the body tubes around. You can have a look at yourself. Basically, the good one is the best one is the split molding one. So split molding is really perfect for the body tubes of the payload and engine section. All right, moving on to the recovery and payload bulkhead. As you can see, they have a shared modular design, which I think is quite neat. They each consist of 3 parts, which is the upper, the middle, and the lower body bulkhead part. They will be glued to the body tubes, and as mentioned before, they basically share the same design, but there are a couple of differences. The first one being that the recovery bulkhead obviously needs to mount the recovery buckle, which the recovery cords will attach to. It also mounts the upper launch lug. On the other hand, the payload bulkhead is going to mount the payload. In that case, what we really wanted to maximize is the maximum diameter that the payload, maximum usable diameter of the payload. So as you can see here, basically this upper part limits the maximum diameter that our payload can have. So that is what we try to maximize with this design. Our result is that our payload can have a maximum diameter of 90 millimeters, which I think we're quite happy with. Lastly, the payload bulkhead will secure the engine through a simple screwing connection. Lastly, we have the engine bulkhead. The engine bulkhead is quite a simple part. However, it will absorb the thrust of the engine, and it will be glued to the engine body tube. It also attaches the bow tail through the use of 6 screws. Oh, sorry, yeah. That's where the thrust will be absorbed of the engine. This is where the launch lug, this is where the bow tail will be attached to, and this is where the lower launch lug is going to be mounted to. This is the bow tail design. As mentioned before, it serves the purpose of reducing drag. Secondarily, it needs to be able to hold the rocket when the rocket is just standing on the ground. It will be 3D printed as well. However, the material has not yet been selected, as we still have some open questions left in terms of heat loading of the bow tail. Obviously, it gets quite hot because it's close to the engine, and also it has a lot of drag going on. So we might use carbon fiber reinforced polyamide, and maybe we will use PEEK. However, this is not yet determined, but those are the materials we were looking at. The minimum diameter is 105 diameters, and this is not secured yet, but maybe we will write a bachelor thesis about implementing a crush core into the bulkhead, into the bow tail design. Would be cool, but at this point it's not quite confirmed whether we're going to do that or not. Moving on to the launch lugs. There's 2 launch lugs, one at the recovery bulkhead and one at the engine bulkhead. It will be 3D printed as well using carbon fiber reinforced polyamide. And the function is to guide the rocket at the launch rail during liftoff. And it also needs to hold the rocket in place. Lastly, we got the fins. We settled on a 4-fin design for easier alignment when compared to 3 fins. The material will be glass fiber reinforced plastics featuring a trapezoidal shape. The manufacturing process will basically go like this. We designed a rig, that's the yellow thing obviously, that's not part of the rocket. The fins, with that rig we can align the fins, and then we will temporarily glue the fins onto the engine body tube. Once that glue has cured, we can remove the rig, add fillets, and then 7 layers of glass fiber reinforced plastic will be added on top. Whoops, sorry. We are quite confident that that will result in a very strong way of attaching the fins. That was basically the deep dive into the structures architecture of this rocket. So the basic design is finished right now. We're working on the finite element analysis right now. And this will all be concluding in a structures test campaign where we basically want to test and validate the entire design. We'll be doing 6 different tests. The first one will be a tensile test where we will take an aluminum plate and a carbon fiber reinforced plastic plate, glue them together, and we will do an entire test series where we use different surface treatments. And our goal is to find a process that reliably leads to cohesion failure versus adhesive failure. Once that is done, we will move on to an entire prototype test of the gluing connection of the bulkheads to the tubes. That will be with a shaker test. We also have another shaker test planned, which will test the modular bulkhead. So basically the threaded rods that you can see right here, and also the buckle. Lastly, we'll do another shaker test, which will be of the nose cone. The nose cone will be mounted in 90 degrees, which will basically be the worst possible angle that the cords would pull on the nose cone during main or drogue parachute deployment. We will do a wind tunnel test with the fins. The wind tunnel test will be a supersonic wind tunnel test at the DLR. This is not, it's looking good, it's not secured yet. And if it doesn't work out, we'll just build a simple rig and do a static load test. Lastly, we are considering a buckling test for the longest body tube, which is the engine tube. However, we're expecting very high safety factors with our finite element analysis, and if the safety factors are exceedingly large, then we will disregard this test to save both resources and workload. Yeah, this concludes into the timeline. Right now we're working on the finite element analysis, and we are working on designing the test prototypes for the upcoming test campaign. Then in December, the test campaign will take place at the SLR here in Aachen, and that will basically validate the rocket's design. We feel quite confident in that plan, and that will conclude into the critical design review in January. After that, we can move on and start to manufacture the finished rocket to hopefully have a nice rollout event in May, and then for liftoff in June in New Mexico. Thanks for listening. We're now moving on to recovery, so I'll leave the stage to Florian. Thank you.
Hi, my name is Florian, and I'm from the Aquila recovery team, and I'm going to talk about the recovery system of our rocket. So what is a recovery system? You heard it, maybe you heard it in the beginning when Tobias talked about it, but boiled down, it's everything that enables the vehicle to touch down safely after it's reached the apogee. In our case, it consists of 2 parachutes, a smoke drogue parachute and a big main parachute. So let's first talk about the cord system. The cord system connects all the different parts of our recovery system: the main parachute, the drogue parachute, the rocket body and the nose cone. Before the initial deployment, and we have 3 deployment stages. Before the initial deployment, all the things are packed really tight together inside the body tube of the rocket. And it will remain this way until apogee. When we reach apogee, the CO2 system will fire and the shear pins, which kept the nose cone attached, will snap and the nose cone will be ejected. Subsequently, it will pull out the parachute hardware out of the body tube, inflate the drogue parachute, and the drogue parachute will help stabilize the rocket on its way down. But we're too fast for the touchdown, so we need to deploy a main parachute. When the drogue parachute, which is attached to the top of the main parachute, pulls on the main parachute, it pulls it out of its bag and lets the vehicle touch down safely. How everything works in detail, I'm coming to later. Now we have the main parachute bag. Its main purpose is to protect the parachute from inflating, protect the main parachute on ascent and descent, or a part of the descent, and from inflating prematurely. It is made of a combination of carbon fiber and ripstop nylon, and in our design, it's very long. It's 1.5 meters long. And this is by design. So this minimizes the time it needs to inflate and minimizes the risk of entanglement during the inflation process. The parachute canopy. Next, we will talk about elliptical design and toroidal one. We chose the elliptical design instead of the toroidal one because it's very simple. The toroidal one has a few benefits, mainly that the drag coefficient of the toroidal parachute is higher, so you can use a smaller parachute, but that's not a problem in our case. So we chose the elliptical for the simpler design. Our drogue parachute is 0.7 meters in diameter, and our main parachute will be 2.5 meters in diameter. The shock cords are manufactured here in Aachen at the Institute of Technology and will withstand a maximum shock force of over 4 kilonewtons. Let's talk about the separation mechanisms. The separation mechanisms are used to trigger the main parachute deployment. We have 3 options. The first option is a tender descender. As you can see here, there's a little cavity you can put gunpowder in, and when you ignite the gunpowder via the electronics, it pushes out this metal piece and releases the buckle and detaches the two shock cords. The second option is a rope cutter. It's a really simple design. You have a metal tube, metal slug, and it's going. The metal slug will be fired into the metal tube, into the rope that's going through this little hole, and cutting the rope, separating it. And the third design is a decoupler design. It uses no gunpowder. It's fully reusable, and it features a motor, a cap, 3 steel balls, and a casing. So when you turn the inner camshaft, the balls drop inside and the cap can be released. A few other parts of the cord system include the protection sleeve. It is used in the lower part so that the cords don't rub on the sharp carbon fiber tube. Swivel links to prevent the twisting of the ropes so that they can rotate freely, and the buckles which attach the cord system to the body tube and the nose cone. So now I will talk about our ejection system. The ejection system is also without any pyrotechnics. It is situated in the nose cone and has two semi-redundant valve system, or is it two? It's a semi-redundant valve system because why is it semi-redundant? Because it just only has one tank. We could just add in a second tank, and if it's necessary, if the testing shows that this is necessary, we can add a second tank without any problems. That fits really nicely into the nose cone bulkhead, as seen previously at the structures section. It consists of a ball valve and a servo motor. When the servo motor turns the ball valve, it releases the CO2 and pressurizes the cavity in which the parachute sits and push out the nose cone, triggering the deployment of the drogue parachute and so on. Now, what is our timeline? We did the first ejection test and it went really well with the help of STAR and their test stand. We will further do tests to ensure that our final system is working. And we are working right now on sewing and manufacturing our parachutes so that we can test the complete cord system, and hopefully it's all ready by the time by the PDR. And after the PDR, we will do some finishing touches, and then we're going to start at the SSE, hopefully. Now I give over to Johan from the Avionics.
Thank you very much. I'm Johann Schepke, the lead of the avionics team of Aquila. And I'm going to walk you through the electronics that we built into our rocket. Our main goals as the avionics team are we want to report back the GPS location of the rocket. After it's landed, it's somewhere out there in the desert, and we need to find it. So we have a GPS tracker in there that's sending back the location. And the second mission critical goal is to trigger the deployment of the parachutes. That means we have two parachute events, the main event and the drogue event, and we need to trigger both in the right moment to recover the rocket safely. Furthermore, you can see we have auxiliary systems. We implemented some additional systems that are not mission critical, but are just fun to have. For example, we have 4 cameras and some additional sensors. So now I'm going to walk you through one by one what we are doing and what we are developing. First of all, our recovery system. Our recovery system is fully redundant. That means we have 2 separate systems which can both do all the functions that the rocket needs to do. On the right side, you can see our self-developed
recovery system, and on the left side you can see a board solution that we are using as a backup if our own system fails. We have an additional layer of redundancy. As you can see on the bottom, we have in total 4 batteries, so 2 batteries per system. That means we have power in any case. On top you can see a so-called arming system. The arming system secures that we are not able to fire the parachutes before we are ready to fire the parachute. That means we only arm the rocket as soon as it's in launch position, and we have no danger of something exploding before that. First of all, we're going to take a deep dive at the self-developed board. Our self-developed recovery board has currently a first working prototype. It's actually quite compact and can do a lot of things. We have a total of 4 high-power outputs, which can trigger parachute events. We have 2 sensors, a barometric pressure sensor and an accelerometer, which both serve to finding out whether we have reached apogee or whether we are at around 400 meters to deploy the main parachute. Additionally, we have some data collections. We have an SD card and a flash chip on board, which both can save the data for further analysis when we are back on the ground. And we are using 3.3 volt as a logic level and 12 volts as the high voltage that's going to the parachute deployment mechanisms. Now we're coming to the board system, the so-called COTS system. We are using a Telemega from Altus Metrum. As already mentioned, it serves as our backup solution, but it also serves as our telemetry radio. That means it has a GPS tracker on board, which is sending back the location to the ground. It runs on 3.7 volts, which is equivalent to a 1S LiPo battery, which we are using. Now we're coming to the arming system. As already mentioned, the function is to disconnect our parachute deployment from our recovery electronics. And we're doing this by the means of switches, which physically disconnect the wires going to the parachute deployments. And those switches are held down during flight by a screw, which secures that they can't be unpressed during flight. That brings us to the next system. Our avionics system, of course, needs power, and this power is provided by 4 batteries, but those 4 batteries need some additional electronics to get the right voltages and the right power. For this, we are using mostly off-the-shelf parts. We are using an off-the-shelf battery management system that protects the LiPo batteries, and we are using an off-the-shelf step-down converter to get the 3.3 volts of logic level for our self-developed board. That brings us to the batteries themselves. We have 2 batteries which are 1S and which provide 3.7 volts for the Telemega. And we have 2 batteries which are 3S and which provide the power for the self-developed system. They are both selected in the capacity that we have around 11 hours of runtime, which should give us enough time to have enough time on the launch pad, during the launch itself, and after recovery, that we can find the rocket out in the desert before the battery runs out. That was it for the recovery hardware, and now we're coming to the telemetry, reporting back the GPS location. For that, we have 2 sections. The first section is on the rocket. The second section is the ground station that's receiving the data. First of all, on the rocket, we have, as already mentioned, the Telemega. It has a GPS tracker on board and a radio, which then sends its data by the means of an antenna to the ground. For the antenna, we have currently 2 options. The first option is to use a simple monopole antenna, and the second option is to use a helix antenna, which provides circular polarization. but we are not quite sure if that's allowed in the SAC because they need to receive the signal as well. So we are developing both options at the moment. On the receiving end, we have a so-called Yagi-Uda antenna. The Yagi-Uda antenna is already built and is proven that it works. So we are using it for its directional and high performance in the field. This Yagi-Uda antenna is connected to a so-called teledongle, which is coming with the telemega. And this teledongle is feeding its data to a laptop, which is running a software which can display and save the data so we can see where the rocket is and where it's heading. That was it for the mission critical stuff. And now we're coming to the auxiliary systems. The auxiliary systems, as already mentioned, are not mission critical, but just some stuff we wanted to have in the rocket to record some extra data and record footage. We have a total of 4 cameras and some additional sensors. For the sensors, we have an additional accelerometer and a temperature sensor in the tip of the nose cone. And we have a dynamic pressure sensor. That's the dynamic pressure sensor gives us the ability to judge the speed of the rocket while it's in the air, which is quite difficult. In the car, you have the reference point of the floor, but in the air, you can't really see how fast you are going. So we are using a pressure differential. It works by taking 2 pressure measurements. The first one is in the front of the rocket, in line with the airflow, and the second one is on the side of the rocket, which is orthogonal to the airflow, and thereby providing us a differential, from which we can derive the actual airspeed of the rocket. At least in the subsonic regime. In the supersonic regime, there are some difficulties doing this. Next up, we have the cameras. As mentioned, we have a total of 4 cameras. And the first 3 are oriented in a way that we have a 360-degree view of the sky. And the last camera is oriented downwards in the separation, in the recovery bay, looking into the recovery bay in the recovery bucket. For the first part of the flight, this camera sees nothing because it's looking into the filled parachute bay. But it's called the so-called separation cam. And that means as soon as we reach apogee and the rocket deploys the first parachute, we can see this event hopefully in full color and 4K. That brings us to the last system of the auxiliary systems, which is power. We are using just 1 battery because it's not mission critical. And we are using basically the same system as before with step-down converters and off-the-shelf battery management systems. Now we have to have something running on our boards. On our COTS board, the telemega is running also COTS software because it has to be something that we haven't touched, so it works. And for the self-developed option, we write our own software, and our board is running a so-called state machine. A state machine has different states which are saved, and it only can progress to the next state that's possible. And it's only possible if a certain condition is met. For example, you can see in the coasting phase, we have the condition to go from the coasting phase to the descent phase is that the current velocity is smaller than 0. And that means we are going down. And but to verify that we are going down, we need something that tells us our current velocity. And that is, in our case, those are sensors, but sensors are inherently noisy. They don't give you the real data, they give you lots of data that's kind of close to the real data. So we need something to filter this data and derive the real value. And for that, we are using a so-called Kalman filter. The Kalman filter takes the noisy data and tries to approximate a solution that's close to the real one. As you can see on the right side, that's our Kalman filter already working. In blue, you can see the sensor data, and in red, the approximation the Kalman filter came up with. And the green is the optimal or the right solution. And as you can see, it's actually coming quite close. So that gives us accurate data and therefore accurate events and therefore hopefully deployment in the right moment. But how do we actually verify that our Kalman filter and our state machine is working? We do that by the means of testing, and the testing is software testing as well as hardware testing, as we are testing on our own hardware, and therefore we are testing both systems at the same time. The first step of testing is using simulated flight data. We can get the data from the simulations team and run that through our board and look at if our board would have deployed the parachutes in the right moment. That stage is already in progress and is looking quite good. The next step is to use pre-recorded flight data. We have some flight data from other teams which have flown and recorded their data and provided it to us, and also the two previous rockets that already have flown in the space team. We can also use their data to feed it through our board and look if our board would have acted correctly. The last option is to use a small-scale test flight. As it's not as important to detect apogee at 10 kilometers, we can also do it at 100 meters. That is what we are currently planning, to conduct a small scale with a small rocket, put our board inside, and look if we can predict apogee correctly. So that's it from the avionics team. So I will give over to Fisnik for some finishing words.
Yes, thank you everyone. We're finished now with the presenting part, so now it's your part. So we're open for questions and feedback. I would say it would be the best that if someone from the Zoom meeting wants to ask a question or add some feedback, he raises his hand with the Zoom command, and then we just pick you, and we'll try to make it 50-50 with a live presence if there are some questions here. Of course, if you are on the Zoom meeting, you can put on your camera so we can see you. We can put you on here so the live audience can see you. And yeah, let's get started with some questions or feedback. Oh, well, of course, German also works, at least for us. Ja.
Jetzt in Deutsch oder Englisch? Die Frage.
Wie du magst.
Okay. Ja, also wie wird denn der Gewinner da ausgewählt bei dem Wettbewerb? Also nach welchen Kriterien wird da ausgesucht?
Genau, also man muss so...
Konnten die Leute jetzt hören?
Ja, das war doch Mikro laut, oder? Ja, okay. Man muss so präzise wie möglich die Distanz richten. Ich sage das nochmal ganz kurz auf Englisch, weil mir ist auch eine Sache aufgefallen, die vielleicht nicht so ganz klar geworden ist. We start in America, so they don't use metric units. So when our simulations say that we reach 9.3 kilometers, that doesn't mean that we overshoot, because the category is not 9 kilometers, the category is 30,000 feet. So 30,000 feet is roughly 9.3 kilometers, so when our simulations say we reach 9.3 kilometers, that's the actual apogee that we want to get. Any further questions? War das klar? Mit genauso präzise wie möglich?
Also es geht nur um die Höhe, also im Endeffekt.
So there are different points you can get, basically. So in the competition, 1 point or several points are for if you reach the apogee as precise as possible. Then you also have payload points and stuff like that. So it's not only the apogee. There are also some other categories.
Okay, meine Frage wäre, also ich habe das jetzt so verstanden, dass die Spitze und der restliche Teil der Rakete beide an dem Fallschirm hängen. Also die stoßen ja dann wahrscheinlich zusammen. Gibt es da irgendwie Probleme oder also, ja.
Yeah, the nose cone is higher than the rocket body, so the shock cone is just shorter. And when they descend, you have the rocket, and you have the shock cord, and then the nose cone, and then the parachute. So it's one after another, not side to side.
One problem that is obvious is that the cord is onto the nose cone, so it wiggles around when it's in the air, but that is what we are going to test in the structures test campaign, what Janus already said. Maybe some questions from the Zoom audience. Is someone raising their hand, someone having questions? All right, we're starting in English. We have some international audience there, so from now on, let's keep the questions in English.
But you can ask in German, and we can translate it.
Okay, Jacob has a question.
Hello, everyone. My name is Jacob Larsen. I am with Copenhagen Suborbitals, and I am also part of the Danish space business as a systems engineer. So first and foremost, I would very much like to thank you and the entire team for a very thorough and inspirational presentation here. It provided a considerable insight into all the efforts that your team has put into this endeavor. And I have crossed out about half of my questions during your presentations here. I don't know if you are up for this, but I have about 10 questions to give you a run for your money if you are interested. I'm not interested in taking up the floor space for everyone else. So I would like to get the opportunity to present my questions as the last one so that I don't take anybody's floor space. You don't have any more questions from the audience right now?
Any questions from the live audience? Doesn't look like it.
All right. I tried to keep it structured into the different sections of presentation, so I hope to be able to group these questions. Some of them will be extremely short, some of them will be a little bit longer. The first one is in the simulations and structures section. One of the things I could not see from your presentation, or one of your initial illustration animation of the flight showed that you received zero velocity at apogee. That is, of course, vertical velocity, but what have your assessments and simulations come up with in the order of lateral velocity?
About 30 meters per second.
Okay. Have you, this is a continuation of that question, have you been considering the effects of a so-called backflip? What has been seen in several occasions is that the lateral velocity is higher than anticipated from the simulations, and the deployment of the drogue chute will cause a significant braking force, which causes the entire rocket to flip very quickly due to changing motion and putting the back end of the rocket first. Have you been considering some of these effects on your recovery system at this point?
I think this might be a question for recovery.
Yeah, we still need to look at that because we not we don't have finally decided on, we don't have the final size of the parachute. This was just an approximation because the weight of the rocket changed so much over the last few weeks that we have to consider this again, but we will do that.
All right, as a continuation of that one thing I couldn't see from your design is, do you have a sharp edge on the opening of your parachute bay? This is in conjunction with the possible backflip that this rocket is going to make. Some of the failure modes that has been seen in these cases are that a sharp lip on the recovery bay either has the potential to actually cut the shock cord, or the shock cord will tear down through the parachute compartment like a zipper, possibly damaging the shock cord in the process. Have you been considering this failure mode?
Yeah, 1 second. We gotta get to the slide.
Yeah, we have a parachute protection sleeve on there. Wait. Where is it? It will be made out of Kevlar, and it protects the cord from, and it protects the cord from rubbing against the sharp edge of the carbon fiber.
Okay, so the protection sleeve extends all over the edge of the parachute compartment and prevents cutting and laceration of the shock cord.
No, it goes over the shock cord, and it will be thick enough to withstand the edge. Yeah.
All right. If we stay a little bit in the recovery area, might I ask you to just recount how your last 2 recoveries on Carl 1 and Carl 2 went?
Can you repeat the question, please?
Okay, let me try and ask it another way. Did you get a nominal dual stage recovery deployment in those 2 prior cases?
Yeah. No, not really. I think with Carl 1, only the main parachute ejected. We actually have someone working on Carl right here. Maybe he could answer the question better.
Yeah, I didn't work on Carl 1 specifically, but I was in the recovery team for Carl 2. So in Carl 1, we had actually a nominal drogue parachute deployment, but what we experienced is that the main parachute was deployed too early, so the main parachute bag was not shut properly, so the main parachute deployed at apogee as well. On Carl 2, we had a different problem that occurred. We closed the main parachute bag using a system that used the tender descender to actually keep the bag closed, but we suffered from entanglement. And the reason for this was twofold. First of all, we had a high spin at the apogee, which probably enhanced the risk of that entanglement happening. Also, we packed the cords loosely inside the rocket body, which is, as we learned the hard way, a large mistake to make. So the current recovery system will employ also a cord management system, which was not discussed in the presentation. The deployment bags are designed to hold the shock cords in place so that we don't have loose hanging cords during the descent phase. So that is a big improvement that we are employing also for the Aquila rocket and also in STAR.
Okay, because that was exactly the other question I was leading up to. It was a trick question, what the specific improvements in this deployment system was to mitigate the unfortunate effects of the last 2 recovery systems. So, as I hear it, a system which keeps the parachute lines in place, and then a different mechanism for the deployment bag itself.
Right, and an additional improvement that was also made is on the main parachute bag. It is not actually a bag, but more a long sleeve. This is a design that was inspired by paratrooper parachutes. So before the main parachute slips out of the deployment bag, it is completely stretched out. So the problem that we had during the Carl 2 flight was that the main parachute got entangled on the cords that were supposed to hold it. So here in the Aquila rocket, the improvement is that the parachute sleeve is long, and the main parachute canopy is fully stretched before the parachute inflates, rapidly reducing the time that is there for entanglement to happen.
Very, very nice. Okay, that clarified a lot that wasn't available from the written material and the presentation as well. You mentioned, it's just the final question in this case here, you mentioned that you've been doing a lot of testing on this parachute system. Which kind of tests? Are you doing only ground testing, or do you have the opportunity or planning of doing drop tests, or what is the testing scheme here?
So the testing is, let's call it a hybrid between ground testing and flight testing, because we designed a parachute sled which is pulled by a glider launch winch. So we can have a mobile test bench to which we attach the parachute, and we can measure force and wind speed. And combining those outputs of the sensors, we can do a couple of things. We can estimate the drag coefficient that the parachute has. This is then used to dimension the final parachute size. And also we can use this setup to test the deployment sequence. It is still not clear if we can actually have the nose cone deployment included in this test, but of course the main parachute deployment sequence can be tested this way. And we are currently planning to conduct these tests early next year.
Glider winch, that is an interesting new idea I haven't heard of before.
There's actually a YouTube video on our Space Team channel. You can
yeah, don't watch that. That shows how it didn't work.
All right.
No, the video mentioned...
That's covering a lot of ground here. So, yeah?
Yeah, sorry. The video that Fisnik mentioned, you can go ahead and get an idea watching that how the system is intended to work, but be aware that at the end we didn't have enough counterweight on the sled itself, so it lifted off. We knew this would happen, but we didn't have enough daylight for another test, so we just went full on, and that might have been a mistake. But yeah, it's a very exciting result.
I think I must watch that one. If we take a small step over to some of the avionics, two questions came to mind. Has the link budget and everything for the RF link looked quite straightforward and with plenty of margin? However, the assessment of over the ground range was a very, very small paragraph in the written material. Have you been doing testing on this telemetry system, or have you planned or carried out range testing in various kinds of terrain with this system?
The telemetry system is almost completely COTS. That means we are planning testing. We are planning to conduct some tests in the area here, but it's not quite easy to find a flat area of that size in Germany. But we are planning a test of 3 kilometers and a test of 9 kilometers. I'm not 100% sure on that, but currently simulations show a circle of around 3 kilometers of maximum downrange movement of the rocket. So 3 kilometers should be sufficient as range testing, but the problem is that we can't do much about it if it doesn't work, because the system is completely COTS and has to be this way. So there are not a lot of options we have to adjust the performance of the system. We can tweak a few features of the Telemega, but we are not allowed to change stuff about it. So that's kind of a problem, and we are hoping that the testing turns out well. But prior testing of other people and the performance data sheet of the Telemega show that it should perform that way. So we are confident that it will.
Hmm. I was just referring to situations where thing goes very much different than nominal. I vividly recall a situation where a rocket, quite like this one, like a real dragster rocket in the 9K category, decided, despite a very elaborate parachute system, to deploy its main parachute at 9.8 kilometers. That put the telemetry system on a whole different kind of work than anyone had figured in the mission description, etc. So it's just, I was just trying to prepare you, your team, that this might go distinctively different than anticipated.
Yes, I have heard some stories from the SAC and the LIROC too, where rockets glided off and were never found again. But we have considered that option, and that's why we are doing also the 9-kilometer test. But beyond that, we don't have much hope of the small antenna to find it. We have another option at the SAC. The SAC provides a service, or you could call it. They have a tall and large antenna mast that can receive your signals, and you can go to them and ask if they received something. So if our small Yagi-Uda antenna does not pick up any signals anymore, we have another option.
Okay. It was just in that bespoke case, the parachute and nose cone decided to land about 27 kilometers away after 40 minutes of descent. So something like this is actually happening in real flight campaigns. The last one, actually, to the avionics section was the commercial battery management system modules. They're really, really nice and very useful. But one thing I didn't see or hear any mention of was the overcurrent protection thresholds. Is that something that has been investigated through either a data sheet or measured with practical experiments, or is it just the assumption that there is an overcurrent protection and that is sufficient?
The overcurrent protection has not been yet tested, mostly because we are hopefully can implement the non-black powder recovery system and therefore have at all times a low current that's being drawn. If we are implementing, for example, if we are implementing a pyrotechnic device, there will be a high current draw at some point. So that's also something we plan to test, whether the performance of, whether the overcurrent protection kicks in before the black powder ignites. But currently we have not tested that yet.
I would strongly recommend that you map out the overcurrent thresholds on these devices and make sure that you have a safety factor of at least 2.5 on the current draw.
Yeah, that's we will do that, and hopefully we will come back with results that show that our battery management systems are sufficient.
All right. That basically concludes it from me. Thank you very much for letting me hijack the floor and grill you a little bit.
I would say thank you for attending. We're very blessed to get your feedback. Something that is probably to be said, that maybe got lost in translation or something. The people working on the Aquila rocket are mostly newbies. We didn't build the Carl 1 or Carl 2 rocket, so we are a completely new team that just got experience from the mentors that worked on Carl 1 or Carl 2. So yeah, we're very blessed to get your feedback. We heard some stories from our mentors, so thank you very much.
You're most welcome.
All right. Are there any more questions? Maybe live audience again. Okay. By the way, this is ne? So this is actually a photo of the sled. Maybe Recovery can say 1 or 2 words on that. So this was how we tested the parachutes.
Yeah, can I show it on the laptop? Yeah, on the front we attached the winch, which would be normally used to pull glider planes, and on the back there will be a load cell and the parachute, so we can drag it down the landing or starting strip for the glider planes and get our data this way. It's I think a really nice design that the STAR team came up with, and we are using it also for the Aquila rocket and to verify our parachutes. Yeah.
All right. Any more questions? Also feedback or something? Maybe you think there are some comments on our rocket. That's the video, by the way. So this is how you test parachutes if you can't do drop tests. So no questions. Okay. If no one wants to say anything or ask anything, I'd say we conclude this with a big thank you. Thank you for attending. It is really important to us to get the feedback as we are going to the critical prototyping phase. It's probably good to note that now we're starting to test the systems. That's the things we are going to do to the CDR. And yeah, hopefully all our safety factors get verified, and we can freeze the design in January. Thank you all for attending, and yeah, we'll see you.